All right, recording is rolling. It's Monday, April 3rd. So I've got a bunch of demos for you guys, and we're going to go through rest of these posters. Okay, so you guys know we have a 4-day week. We have a Good Friday off. Also, I'm not going to be here tomorrow. I always hate miss school, but just got stuff I got to do. So you guys going to have a substitute. We set you guys up with a radio lab, so you guys get to exercise your auditory skills, listen to a science story, with Radio Lab. Right, so here, we're gonna go through these posters. I'll show you guys some other things that you can put on a circuit other than just resistors and a voltage source, right? Which is what we've been focused on so far, right? What are capacitors and inductors? What are those useful for? Got some polyhue demos for you guys. And so let's get going. Should give you guys a quick recap of some stuff from last week just to tie in and remind you guys what we've been doing. So back a few days last week, I had you guys doing the circuits page here. Pulled up most of the circuits from this side. We did skip these last two, so don't worry about those. But most guys already turned this in. If you haven't turned this in yet, just figure out these except for these last few circuits. And then we did all these waterfall models on this side and the corresponding Kirchhoff tables. So you guys remember if you have, say, 3 resistors in series, for example, like here, the voltage drops are going to be a little bit, but they have to add up to match the voltage of the battery. That's called Kirchhoff's loop rule. Versus if you have something like this, where 3 resistors might be in parallel. Back up. I forgot to mention the current has to be the same everywhere, right? So it's the same current everywhere, right? For 3 resistors in series. Right. Now let's switch over to 3 resistors in parallel. Now for this one, the voltage drop has to be the same across each one, which would in this case match the battery. Okay? Even if they're different resistors, if the resistors are different from each other, then you have different currents. That's okay. Like the more resistance, the less current will flow that way. Okay? But the current does have to add up, right? So according to the junction rule, right? So if it's like 3 amps plus 4 amps plus 5 amps, that might add up to 12 amps, right? For example, right? Right. And then we did some complex circuits where there's a combination of series and parallel. You guys saw this with the Christmas lights too. You guys remember the cell phone chargers and the Christmas lights? You guys hooking them up different ways, right? Saw different powers of brightnesses. How do you measure the voltages and the currents? Right? So you guys use the voltmeter and the ammeter features of the multimeter. I come those ways. Right. Okay, so that's all from last week. Okay, any questions so far? Before we start seeing some new stuff? Right. All right, so what are some other things you can put on a circuit? Right, so here's the voltage source, and here's the resistor. That's been our main focus so far. Okay. You could put a fuse on your circuit. It's a symbol for that. Now, the purpose of that is for safety. So suppose there's like too much current going through, like too many amps, that will blow the fuse and it will cut the circuit open, and then the electricity stops flowing. Okay. So, for example, what if you plug in an appliance and you accidentally touch the metal part, and then there's this huge surge of electricity that starts going through you? Well, that would be bad. So, if there's a fuse in the mix, then that current will overload and it will break the fuse and it'll open the circuit. Now, should you have a fuse connected in a circuit, should that be in series or parallel with the rest of the circuit? Series, has to be series, exactly like it's shown up there. Because if it was in parallel, it would be completely useless. Like here, if I had another resistor going this way, then the current would just flow around there. It just broke open, right? So the fuse is going to be in series, exactly like it's shown here, because that's the only thing that makes sense. Right? So blow the fuse, again, that's for protection, right? Okay, so you guys also have, inductors and capacitors we're going to look at. We'll look at capacitors first and then inductors. Okay? That's also, if you might remember, these 2 lines that we skipped before down here. So capacitance can be measured in farads, coulomb per volt, and inductance can be measured in henries, something like joule per amp squared. Right? So we'll look at those later today. Right. Let's look inside a battery. How about that? And so a battery could be an example of how you can store energy in a chemical form. And so you need an anode and a cathode. So for those, you could use, for example, zinc and manganese dioxide. That could be your anode and your cathode, maybe separated by an electrolyte inside the battery. So the potential difference between these 2 materials could be 1.5 volts. Right? So pretty close to that. Right? And then, all right, so they connect this positive to this negative, hopefully going through a resistor, and then get the current to flow. And eventually, there's also a chemical reaction inside the battery. So Right, so we'll look at capacitors. I got some video demos. You guys can see what's going on with these. So capacitance could be charge per voltage, and the capacitor is literally just two parallel plates. You guys see a Leyden jar version of this that Ben Franklin and friends were playing around with back in the 1700s. So two parallel plates. Okay? And if you get a current flow through here, then there will be a charge that builds up, and uh, so these things will happen. So there can be energy stored in the capacitor. Right? So 1/2 times the capacitance times the voltage squared. Okay? And it will also cause the voltage to lag in the circuit. So if you have one of these in the circuit. Okay? So back to the circuit, we're looking at this right here. So two parallel lines, so same length. It could be a capacitor. That's the symbol for it. Okay? It's pretty well what's going on. Okay? So if you hit an on switch, it takes a while for the voltage to build up. And if you hit an off switch, then it takes a while for the voltage to dissipate. So this is sort of a kind of like a battery in a sense. They can store energy temporarily, but it's in a electric field rather than chemically like a natural battery is. Okay? If you have an electric appliance that you unplug from the wall and then you start taking it apart, so you break out a screwdriver and I want to take apart this whole TV set, see what's inside it. Okay? You have to be careful because if it has some capacitors in it, good chance it does, then might store some energy and it can still shock you, even though it's not plugged into the wall. Right? If you're playing around with the components, there could still be energy stored and it could still give a pretty good shock. Okay? Inductor. Right. So here's this. Oops. Back to this. This curly looking symbol. Okay. Right, this guy right here. Right. So that's literally what it is. It's just a coil of wires. Oops. He's out of order here. Okay, here. So if you have a wire coiled around, and then you run electricity through that. Now, if you're changing the direction of that current, what I'll show you guys later is that's actually going to induce a magnetic field. This is also called an electromagnet. I want to have you guys build this probably Thursday or late this week because it's not too hard to make an electromagnet. You just need a current flowing through a coil of wires. Okay, break out right hand rule later today and show you guys that too. Right, so what's the inductance? What's the voltage divided by the rate change of current? Oh, interesting. There's like rate change of current involved. Okay? So if you flip an on switch, then it takes a while for the current to build up. It's like the current's going to lag. And if you flip an off switch, then the current will still continue to flow, but it'll dissipate over time. So it takes a while. So you can store energy this way too. It takes a while for the current to flip on and off. Oh, I forgot to point out the series and parallel. So for inductors, it follows the exact same rule as resistors. If you have two inductors in series, then the equivalent inductances, you just add them. Okay? And if they're in parallel, then you treat it like two guys painting a fence. Okay? So product over sum. Okay? But that was not true for capacitors. Let me go back to capacitors. Okay? So if you have more than one capacitor in a circuit, now this way you guys see the rules are backwards. So if there are two capacitors in series, you actually treat that like two guys painting a fence. So like product over sum. Versus two capacitors in parallel, that's where the capacitances is actually add. Okay, so see some of those later. Okay. I don't want this one yet. I didn't want to save this guy. All right, let's look at this. Okay. So right hand rule for electricity. You guys remember with torque, there was also a right hand rule. So right hand rule for electricity is a different variables, but okay. The similar idea that if you know the directions of each of these variables, then if you have two of them lying around, you can get the third one. So if you run a current past a magnetic field, that's what so you guys know I is current, right, measured in amps. B is magnetic field. You can quantify magnetic field in Tesla. Okay? If you run a current past a magnetic field and they have any kind of perpendicular component, then that will create a force. That device is called a motor. That's what a motor is, right? If you run electric current past a magnet, it will cause some kind of physical motion, some kind of mechanical motion, right? Maybe like turn a ceiling fan, for example. Right? But you can also rearrange these and get other things. So this is if you force a wire past a magnet, that will generate a current. Oh, hey, that's what a generator is, right? So if you have just a wire lying around and you have a magnetic field, so you have a magnet, okay? And so you hook one of those, either the magnet or the wire, so depending on which way you want to build the thing, okay, to a turbine, and that turbine say like forces one past the other, okay, that will generate electric current. Okay? The third thing you can get from this is electromagnet. That's if you take a current carrying wire and force it into a loop, right? Now back to like electromagnetic inductor type thing, right? You get a magnetic field. So if you have any two of these lying around, the third one can pop up, as long as they're aligned with some kind of perpendicular component to each other. Okay, okay. So a generator and a motor, if you've been kind of following this, are actually sort of the same device, just they do exactly opposite things. Okay, so a generator, you can take mechanical energy and convert it into electrical energy. A motor, you take that electrical energy and convert it back into mechanical energy, but their internal components might be like exactly mirror uh, versions of each other. Okay, so yeah, if you force a wire past a magnet, right? Now in this case, I've got this water wheel physically turning a coil of wires through a magnetic field. But you can actually have the other way too. You can have the magnet spinning. That's okay. Have the wire stationary. But something's got to be moving past something. Okay? That will create, that'll generate a voltage according to Faraday's law. I'm about to show you guys, which will create a current. Okay? And then on the other end, if you have a current, run that past magnetic field, break out right-hand rule. Now you have a force, so you have a motor. I want to have you guys build something like this later this week too. At least a simple version of that. Okay? Let's look at these solar pushers here. So Faraday's law. So how much voltage would be induced if you know what your magnetic field strength? Look, I have some version of an inductor here, right? Got a coil of wires. Right? So if you run this magnet past this coil of wires, actually you'll feel a resistive force. Something called Lenz's law. I'll show you guys that too. I have a demo about to show you guys. Right? Create a resistive force, and it'll induce a voltage in this wire. It's this one continuous wire, right? Now, what is that voltage? I've been using capital V for voltage, or sometimes delta V, like potential difference for voltage. But some textbooks use this Greek letter epsilon, so I just went ahead and threw that in the mix too. So if you open up a physics textbook, you see epsilon in the electricity section. It's talking about a voltage, potential difference. Okay? And so where do you get that from? Well, get it from a rate change in flux. That's what this is. D flux over dt, right? Rate change in flux times the number of coils in the wire. So what is flux? Right? Maybe I need a separate poster on that. That's just magnetic field times the area. So if you know the strength of your magnetic field, right? So here's my magnets, here's my field. Right? So how strong is this magnetic field? Here's what magnetic field lines look like, right, north to south. I'll show you guys that too. I have demos for all these. And you are moving that in and out of this coil wires, right? Well, whoops, back, whoops. Okay. So magnetic field is just B, right? Times this cross-sectional area A, that's what flux is. Flux is B times A. Okay? This Greek letter phi, so in this case B times A. Right now, if that changes, so if you're moving the wire, okay, that's what's going to generate this voltage. Right? And the more coils you have, the stronger that effect is. So you'll actually feel a more and more resistive force if you have more coils of wire, and that will create a stronger and stronger voltage. Okay? So N is the number of coils. Right? You guys got that? Oh yeah. Yeah. Okay. You know what? Got to break out a demo. Oh, here it is. I got it right here. I got this right here. Okay, so I have this this copper tube. It's got some magnets in it. Pull the magnets out. Right, so the magnets right here. Show these are magnets. Boom, magnets. Right. So we got some magnets. Now, can you pick up American coins with magnets? American coins. Here's a quarter. No, doesn't pick up at all. Right. Doesn't care. Can I pick up a penny with a magnet? No. Right. So pennies are made mostly out of zinc, at least the modern day ones. If you go back, if you find a penny before 1982, it's made out of mostly copper, right? But copper and zinc, neither of those are ferromagnetic, so you can't really pick them up with magnets, right? This is copper. Okay? All right, so there's like no interaction here, right? No interaction. It's copper and zinc. Okay, so I dropped magnets. They follow the rate of gravity. Okay, so no spread. But I put these magnets inside this copper casing. Okay, and it's got a window in it. Okay, and turn this, see if I can get it so you guys can see it and also shows up on camera. Okay, so I'm looking at this window. Okay, I have to shake this for force the things down. You guys see these magnets really slowly coming down? Great, really slowly. Here, turn this, it's like vertical now. It's like taking forever for these magnets to fall through. It does, right? So they'll eventually reach the bottom, but it takes forever. So why is that? There's some kind of resistive force going on, and it's not from the magnets directly attracting to this to this copper casing. Okay? and it's not really static friction either. I mean, there might be a little bit of friction, but it's not primarily what's causing that, right? Like if the magnetic field turned off, these would just like just fall down really fast. So what's going on? Well, as the magnets are falling through this casing, uh, it's creating a voltage, according to this, which is creating current, uh, uh, which is these called eddy currents, will create its own magnetic field, which resists the original magnetic field of those magnets that are falling through. Okay. All right. So let's call it Lenz's law. It's called Lenz's law. I've got a video demo of it too. That's a little bit better than that too. So I'm good to see that. But it's actually consistent with conservation of energy. Suppose you're trying to generate electricity that way, right? That's how most electricity is generated. You force a magnet past a loop of wire. Well, there's going to be some kind of resistive force there, which means that it takes some work to run the wire past the magnet, right? Which means that that's energy that can be transferred onto the grid. So it's consistent with conservation of energy. Okay. Inductive coupling. So I have a red wire here, and completely separate, I have a green wire. Now, so here's an inductor, and here's an inductor. Okay? Well, I've been telling you guys, again, I've got demos to back this up too, so you guys will get to see these demos later. That if you force a current into a coil like this, it's going to create a magnetic field. Hey, do you think that this guy over here is going to pick up that magnetic field? And do you think that that will, in turn, induce a current on the side? Ooh, so you can get wireless transfer of electricity. Now, when you do that, if you have different numbers of coils, there's actually different voltages and currents that transfer from one side to the other. This is how you can step up and step down voltages, which is really important for transmitting electricity over the grid, right, with alternating current. So the current and power lines might be like 100,000 volts, for example. So you have like 100,000 volts. Okay? But when you're transferring electricity into a building, maybe you only want, say, 120 volts or 240 volts, right? You want like hundreds of volts. Okay? So you have to step it down. So how do you step down the voltage? Well, you do it with a transformer, which is just inductive coupling, right? So you guys know V is voltage, you guys know I is current, N is the number of coils. So if I know the number of coils here and the number of coils here, okay? So voltage will step down proportionally to the number of coils. So if I have like 100 coils here and only 10 coils here, then the voltage should step down by a factor of 10, right? So you get 1/10 of the voltage. Right? Now, current does the opposite thing, but if you think to Joule's law, power is current times voltage, that would make sense. Because if energy is conserved, it's the same amount of energy, right? Then whatever the power is in watts, that's just energy per time. Well, that would also be conserved, right? In this case. If the voltage is stepping down, then the current would have to step up to compensate for that, right? So the current that flows is actually inversely proportional to the number of coils. Right? So on the left side, I might have a huge voltage. On the right side, a small voltage, stepping down the voltage. But the current's doing the opposite thing. So I have a really small current on the left side and a huge current on the right side. Okay? What that's sort of analogous to is, say, like, say you're transferring alternating current over a giant electric grid. Okay? It's like if you had a giant tank of water, right, that was really deep. Right? So really deep means a lot of pressure. That'd be like a lot of voltage. Right? And then if you opened up a pipe right here, right, and the water started like pouring out. Okay? So now it's flowing, and now you have a huge flow rate. That's kind of like having a large amount of current, right? So like the current in the stream, right? Although there's not a lot of current over the lines, the power lines. There's a little bit of current, but it's mostly huge voltage. But then you tap into a building, and now you have the current actually flowing. Okay? Sort of analogy going on there, right? And this is important in alternating current. Right? You step up and step down voltage and current easily that way. All right, speaking of alternating current, let's get a three-phase alternating current. So I told you one way you can generate electricity is to have a rotating magnet. A little bit different than the picture I had earlier, but you can do that. Oh, look at all these inductors. Hey, that's coils of wire. Okay? And then as this magnetic field swings by, we have north and then south and north and south, so it pulses back and forth. You guys see pairs of inductors here, pairs here, and pairs here, and then it connects. Say I have a bunch of voltmeters, and I want to measure what is the voltage. Okay? Well, alternating current means, well, it's going to alternate. So you get like these sine curves, well, sine or cosine, how you look at it, right? So like up, down, up, down, up, down. Okay? Now this is where there have to be standards for an electric grid. So you guys know in North America, or let me see if you guys remember this. What voltage does this go up to in North America? 120 volts, 120 volts, right? And what is the frequency, which is related to the time period? So like how many times does it cycle per second? 60 hertz, 60 hertz, right? Okay, so here in the States, we're on 120 volts and 60 hertz, right? Okay. Now, if you think about it, it's like, well, if this is really oscillating up and down, then at some point the voltage goes to zero. So if you had like a super slow-mo camera, you would see lights flickering all the time. They flicker, 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 right? So to kind of get around that and say, well, let's use like 3 phases so that it like cuts out some of that. It's kind of compromised. Like the more phases you have, the less the flickering is going to be, the more like solid this line's going to be, right? But it's also like more materials to build like more lines and stuff. So it's kind of a trade-off. So 3 phases is what from an engineering point of view. Okay. Oh yeah, yeah, I got it. All right. Let's see. Oh, you know what? I do have some other demos here. Sorry, let's see. Okay. So got this Faraday flashlight. Okay. And what's got in it? It's got a magnet right here. I think this is a neodymium magnet. It's really strong magnet. It's all shiny looking. And then, oh, look at that. A big old coil of wires, okay? So if you shake this back and forth, okay? Now I'm putting energy into the system from my hand, right? Mechanical motion in my hand. There's some kind of force times distance, okay? That's forcing this magnet past this coil of wires. But there's some kind of Lenz's law, resistive force going on, right? And that's charging this up. There's no conventional battery in here, but there is a capacitor. Hey, capacitor that could store energy in the electric field, and then boom, light turns on. Same thing here. So it's the same type thing. Oh, I got a generator in here. So as I rotate this, ooh, I feel like a resistive force. That's good. There's a magnet running past a wire in this generator. And then let's turn on. Yeah. No, this one, I don't think this one has a capacitor because as soon as I stop rotating, it stops turning on, right? Turn on that way. Yeah. So same thing there. All right, let's flip over and get some demos here. Some demos.